So the first lesson was all about just reciprocal functions, okay? And we're moving on to something else, and we're going to spend about 4 or 5 lessons on this, which kind of makes up the bulk of this part of the unit. And as I said, then after that we do some solving of equations and inequalities again. So that day on reciprocals is kind of a one-off, but you'll have a quiz on it, so it's not something you can forget. And remember, it just comes down to the ones and the negative ones, the asymptotes that go through the x-intercepts, and then that idea of as one graph is getting small, the other one's getting very large because one is the reciprocal of the other. We're moving away from reciprocal graphs. These ones that we're starting to explore now are rational graphs, or rational functions, not reciprocal functions. Okay, so they're quite a lot more complex, and they are very different in how we're going to be sketching them and that kind of thing. When we get to sketching, which we will in the next lesson, this is just exploring some properties. This work that we're doing right now is developing properties or gathering properties from an equation that we're going to use to sketch. So when we sketch, what you're going to do is you're going to spend a whole bunch of time, and originally these sketches can take up to like half an hour. When you get better at them, they don't take that long, but they're fairly big problems, right? They can take up 1 or 2 pages of work. So you're doing all these different things to get the properties from here and other properties from here and other properties from here and other properties from here, and you get all those properties done, and then you take them and put them all together and turn them into a graph like that. These are the kinds of functions that we will be sketching, okay? And so you can see that they're fairly complex and they've got a lot going on, and they can look a lot of different ways. We're going to look at that a little bit later. Okay, so what we're really going to talk about today is asymptotes and behavior around asymptotes, which we sometimes refer to as end behavior or behavior around the asymptotes. Okay, so end behavior for polynomials only took sort of one kind of form. They either went off this way or they went off that way, right? That they didn't do anything else. These functions do lots of other things. Okay, they have different types of end behavior, and because they have asymptotes, they have more end behaviors, more behaviors around asymptotes. So there's a lot more going on, and there's different things that can happen. And what we're going to do is we're going to learn how to find the asymptotes, and then we're going to learn how to sort of do some testing to see what the function is doing around the asymptotes. That's what this is all about. So vertical asymptotes, you've seen these before. You've seen horizontal asymptotes before. But again, there's going to be different in how we look at them. A vertical asymptote is a straight vertical line that a function approaches infinitesimally closely. That's like infinitely small distance between the function and the asymptote, right? And it gets smaller, and it just keeps getting smaller forever. The further you go along the line, it will always continue to get closer, but never touches. They are of the form x equals a. And a is a 0 of the denominator of the function. So let me show you what the equation of these functions looks like. There's a good example there. So it's rational because it's a polynomial over a polynomial. And that's what we call rational, like a rational number, like a fraction, right? That's what it's referring to. Okay, so the denominator is a polynomial. That polynomial on its own has zeros, which would be x-intercepts. When the polynomial is in the denominator of a rational function, those are not x-intercepts. Those solutions to that individual polynomial will give us the vertical asymptotes. Okay? Let me get back up here. And so and these are all things that obviously you are going to need to know how to do. You need to know how to find where to find the asymptotes, how to find the asymptotes. And again, that's what we're going to start now. But you'll be doing a lot of this because we're spending a lot of days on sketching. So by the end, it'll all feel pretty familiar, I think. A horizontal asymptote is a straight horizontal line, obviously, that a function approaches infinitesimally closely. Again, gets infinitely close to the function or to the asymptote, but never touches. They are of the form y equals b, where b is the number the function approaches for very large positive and negative x values. So again, let me go and take a look at this graph, and we're going to take a look at the vertical asymptotes first. Notice how it's getting closer and closer. As I move closer x values to the asymptote, the y value is going where? Yeah, it's going up, and it's going like to infinity, right? And it's never going to touch whatever this is. It looks like maybe it's 8 or 9. It's never going to get to that, but it will keep getting closer. And it's got to have somewhere to go, so it keeps going up, right? And this one's approaching from the left, it's going up. And this one is approaching from the right and going down. Okay? And this one also is approaching from the left and going up, and the other one from the right is going down. But they can do all kinds of things, which I guess is part of what makes this tricky, is that when you start a question, you won't know what they do, and you can't just guess. You have to figure it out. Okay? So that's vertical asymptotes. Look at what's happening with the horizontal asymptote. So a horizontal asymptote is as x is getting very, 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 very large. Negative 20, negative 30, negative 40, negative 100, negative 1,000. It keeps getting larger and larger and larger. And this is coming down and approaching, and it's going to get really, really close, but never touch. And this one is approaching from above, because it's above the asymptote, right? And they're not that close yet. At negative 20, they might not be super, super close, but as you get out to negative 100, it's going to be really, really close. And this one is as x's are getting very large positive. See all the nonsense that happens in the middle of the graph? There's vertical asymptotes, there's x-intercepts, there's all kinds of things happening. But then it all settles where the horizontal asymptotes occur, and the graph just kind of, like settles and just goes almost straight along the asymptote to the right and along the asymptote to the left. Okay, and so as x's are getting very, very large positive, again, it's approaching that asymptote, and this time it's approaching from below. Okay. Horizontal asymptotes, I'm reading this bullet here, only occur, this is important, this is something you're going to need to know, when the degree of the numerator of the rational function is less than or equal to the degree of the denominator. So they're equal, or the denominator has a larger degree. We're talking about polynomial over a polynomial, so we're still talking about degrees of the polynomials that are involved in the question. Okay? Make sense? Next one is an oblique asymptote. So we're not going to get to oblique asymptotes for a couple of days, but we will get to them eventually. An oblique asymptote is a straight line, but it's not horizontal or vertical, so it's like diagonal. Okay? And again, it's a line that the function approaches infinitesimally closely but never touches. So because it's a diagonal line, it's like a linear function. It's of the form y equals mx plus b. That's what the equation of an oblique asymptote is going to look like. Now, there are actually other kinds of oblique asymptotes. And when we get to them, I would encourage you, if you're interested in this stuff, to think about what they might be like and how you would create one. But anyway, the ones we do are going to be called slant asymptotes. We only do the ones that are straight lines. And slant asymptotes, the oblique asymptotes that we do, will only occur when the degree of the numerator in the rational function is exactly one more than the degree of the denominator. So if you have degree 3 over degree 2, you have an oblique asymptote. Okay? And so that's why you have to know you either have oblique or you have horizontal. So you need to know how to determine which one it is. And eventually you will, once we've kind of looked at all of it. What would happen if the degree was more than 1, more than the denominator? Well, again, that's something that I would encourage you to think about maybe when we get to oblique asymptotes. Something we're going to talk about briefly if we get a chance is a hole in a function. If not, then when we see holes, you can come back and see it. But this occurs when there's a common factor between the numerator and the denominator in a rational function. Okay? And holes are kind of interesting, so when we get to them, we'll talk more about them. Today we're really just looking at asymptotes and behaviors. So end behavior, as we already know because we've done this, is where do the ends of the graph go? So they're either like polynomials, they're either going off into sort of the corners of like into the quadrants, or the ends of the graph as they approach asymptotes or that kind of thing. Okay? What do they approach? So what value do they approach? From what direction? that kind of thing. Okay? So very quickly, you need to know how to find a vertical asymptote. I'm gonna ask you soon. And hopefully somebody will remember. Vertical asymptotes occur where the bottom of our rational function is equal to 0. That's where you get a vertical asymptote. They are relatively easy to find, so we don't really need to do any teaching on that or any exploring that. They just happen when the denominator is 0. And we saw that yesterday with reciprocal functions, where when we took the reciprocal of an x-intercept, which is 0, you get 1 over 0, which is undefined, and you can't do that, right? So we saw that kind of yesterday, and it's going to be the same today. Now, horizontal asymptotes are a little bit trickier. Finding them is actually quite easy, and I could just tell you how to find them. But I think it'd be more fun if we explored it together a little bit to see if we can figure out what's happening. And we're going to use a couple of little math techniques that are useful to know, especially one that you've probably never seen before. But it comes up in other areas of math as well, so it might be neat to have seen it before. But first what we're going to do is we're just going to sort of ask the question, what happens when x gets really, 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 really large? And we're just going to kind of play around. None of this is a formal proof, by the way. We're just kind of exploring. Okay? Before I actually start getting into it, I'm going to do this. We've talked about this before, but I didn't make you do it. But starting now, you have to. If you're given your function in terms of y, often function notation is very useful, as opposed to having it just as y equals. So if you're given this, not in function notation, with respect to y instead, then I think you're going to want to do this. Let f at x equal y. So on a quiz or a test, if you're doing something like this, yes, you have to put that. If you want to use function notation, you have to put that. Otherwise, you're not allowed to use function notation. And that's just kind of a form thing, but try to get in the habit. Somebody give me a large number, a large negative number.
Negative 97.
Bigger.
Negative 1,000.
Negative 1,000, I like that one. That's pretty big, right? Let's start with that one. So f at negative 1,000. I'm just subbing it in. Oops, plus 3. Over negative 1,000 plus 2. Now I could actually solve this, and maybe we will in a minute. But I get negative 2,000 plus 3 and negative 1,000 plus 2. And I could sub that into my calculator. But we just chose this value. We could have chosen a bigger value for x. So this is going to be about negative 2,000 over about negative 1,000, right? Right? Well, what if we went bigger? What if we went up to negative 1 million? That'd be about negative 2 million over about negative 1 million. Like, do the 3 and the 2 really matter that much? Yes?
I just have a question. Why does it have to be negative?
Because I just chose to start with negative.
Okay.
So, like, the 3 and the 2 don't matter as much. Like, if I just want an approximation of it, like, imagine those numbers getting bigger and bigger and bigger. The 3 and the 2 become more and more and more insignificant. Negative 2 million over negative 2 billion over, like, negative 2 billion plus 3? Who cares? Who cares about the plus 3 if we're just estimating? Do you understand what I'm saying? So this is approximately negative 2,000 over negative 1,000, which is approximately what?
2.
2. Now, if I actually did this, this would be negative 1997 over negative 998, which is, oops, approximately 2.001. So even at 1,000, that's pretty close to 2, isn't it? You had your hand up before. What did you want to say?
No.
You were going to say something like that. Okay, so it's about 2. And remember, a horizontal asymptote is as the x's are getting very, like the x's will get to negative 1 billion. So it'll be negative 2 billion over negative 1 billion, approximately. Like, who cares about the plus 3 at that point? Okay, what about if we do positive? So that is 2 times 1,000. Oh, I want to cancel those out because they are kind of irrelevant. 2 times 1,000 plus 3 over 1,000 plus 2. And again, we're imagining, because you can't actually cancel those numbers out. Like you're not actually allowed mathematically to do that. But what we're doing is, it's like a thinking experiment. We're imagining those numbers getting bigger and bigger and bigger, recognizing that the constant becomes more and more irrelevant. The constants are what make it not 2, and it never will be 2, and that's what makes it an asymptote. But if we're just approximating, they become more and more and more irrelevant. And so again, this is approximately 2. So what does that mean? That means for this function, the horizontal asymptote is y equals 2. Right? That's what that means. It's approaching 2. But what we need to do is we need to find out, without doing this, because I don't want to do this every time. You could do this. Without doing this, is there a way to figure out what the asymptote is? Okay, so hang on to that, because I'm throwing the question out there right now, but I'm going to actually ask it in a little bit. I'm going to show you one other technique where we can do kind of the same thing. And again, it's just something that comes up once in a while in mathematics, so it's a neat little trick to know. So we're going to start with the function 2x plus 3 and x plus 2. And I'm going to multiply this function by 1, but I'm going to do it in a convenient way. So it's going to be times 1 over x over 1 over x. So this is a little trick, and you did stuff like this with identities and trigonometry and that kind of thing, where you multiply by 1 in a convenient way. If you don't remember, don't worry. Okay, so when we multiply that through, I get 2x over x plus 3 over x over x over x plus 2 over x. Well, 2x over x is 2 plus 3 over x. X over x is 1 plus 2 over x. And now we do the same thing. This is just another form of the original function. Okay, so it's not helpful until we do the next part of it, but we haven't changed anything. It's the same function, it just looks different. Now we do the same thing with horizontal asymptotes. We imagine x getting very, 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 very large. What happens to those two things as x gets very, very, very large? This is one of the things we talked about yesterday. The whole fraction becomes much smaller. Gets small, small, small. Imagine the x being 1 billion. 3 over 1 billion is almost nothing, right? 2 over 1 billion. 3 over 1 trillion is even smaller. So these parts are going, as x gets bigger and bigger, those parts go to 0. They never will equal 0, but they get very, very close to 0. And then this will approximate 2 over 1, the parts that are left. So see how that multiplying by 1 over x over 1 over x kind of let us use that little trick of making part of it vanish? If you study math in university and when you do limits, you might see more of that. Okay, so let's get down to it. What's the easy way to figure out what a vertical asymptote is without doing all that testing? But the way you could figure this out is imagine if you did that same testing to this one, right? What would happen?
Can you like divide the coefficient so 3 over 2?
That's it. Yep. The coefficients, right? So 3 over 2, the horizontal asymptote is y equals 3 over 2. Now there are a couple of circumstances where it's a little bit trickier than that, and so you do have to remember, but it's that easy. Okay? You have to know it. If you get to the test and you don't know how to find a horizontal asymptote, you're done. But it's that easy. So you don't need to know all that thinking stuff that we did. You just need to know how to find a horizontal asymptote. Any questions? What about this one? So the first one was linear over linear. This is quadratic over quadratic. The degrees are equal. Didn't we say that's a condition in the instructions at the beginning, or the definitions at the beginning, that when the degrees are equal you have a horizontal asymptote? Yes, it did. So what's going to be the asymptote for this one?
53 and 3/2.
So good idea, you're looking at those to get the 3, and then those to get the 3 over 2. And if I told you a graph only has one horizontal asymptote, or at least these graphs only have one horizontal asymptote, which one do you think it would be?
When you just do 3, because technically like the 6x could become like a lot smaller than 4x.
Nice thinking, that's right. So I could do the same tricks with what we did above and realize that because I'm squaring the number, squaring 1,000, squaring 1,000,000, squaring 1,000,000,000, that's what's going to take over the whole function. And even this part will eventually become kind of insignificant. Okay, so the horizontal asymptote is 3 over 1, or 3. And you always look to the highest degree term over the, right, to get like the coefficients of that to get the asymptote. Everybody got that? What about this one? What do you notice that's different about this one?
The top doesn't have the next square term.
Yeah, they're different degrees. Lillian, I think I know what you were going to say. Were you going to say it's oblique? Is that what you're thinking? David, what do you think?
It's the other way around.
But it's the other way around. You're right. But good on you for remembering. Oblique is when the top is one bigger. This is the bottom is one bigger.
Could it be 0?
Why would it be 0?
Because you can add a ghost term of 0x squared.
And that's exactly what you would do. And that's why there's that little space there. It's kind of a tip. It's kind of a hint, right? But that's what you would think of, and that's what you would have to do. And so our horizontal asymptote is y equals 0. So if you have a bigger degree on the bottom, it will just always be y equals 0. Again, that's something you need to know. Okay? But in a nutshell, that's horizontal asymptote. It's pretty straightforward. Questions? Okay, so next we're going to do an example, if I can find it, where we're going to find both horizontal and vertical asymptotes. Yep, it wants us to do both. And we're going to see what it looks like to test to get the behavior around the asymptote. This first one, we're going to do a little bit of extra writing, and then we're going to do one more where I'll show you what you actually have to write. And we're going to be learning a little bit, some new notation kind of thing and learning how to write it. So the way that you show your work and the way that you write it is going to be very important, partially because these questions are big and you need to keep it concise and clear. And partly because it's the notation that we use and it's the way that we write it and you need to learn it. Okay, so that's something you're going to be thinking of as well. But we're going to do a lot of these together, so as long as you try to be doing it the way I do it, you'll be fine. Okay, let's start with the vertical asymptote. We usually start with the vertical asymptotes for some reason. You can have more than one vertical asymptote. You can have lots. You can only have one horizontal asymptote. What's the vertical asymptote?
X equals 1.
How'd you get that?
Because it's like the finding the x-intercepts like that we did before
Of the
of the bottom.
bottom. It's where the bottom equals 0. Remember I said I was going to ask you that again and you had to remember it? Vertical asymptotes occur when the bottom is 0. There's a lot of different things. So if you get them all mixed and muddled up, that's what happens. There's lots of parts to this. So you want that to be solid, solid, solid. Vertical asymptotes occur when the bottom is 0. When is the bottom 0? You can think of it like an x-intercept. Okay? Okay, and now what we're going to do is we're going to pick some values that are very close to the, so for a vertical asymptote, don't copy this down. I get, if this is x equals 1, actually, maybe we will copy this down. I'm going to do a proper sketch over here. This is what happens with a vertical asymptote, right? No. I'm going to be approaching it from the left and from the right. Only once each. If I'm approaching from the left, I might go up, or I might go down. We have to figure out which one. If I'm approaching from the right, I might go up, or I might go down, and you could have any combination of those. But you don't ever have two asymptotes from the same side, because that wouldn't be a function. Okay? So you have one from the left and one from the right. Which one is it? What are numbers just to the left of that asymptote? And you might want to say 0, but 0 is not close enough to actually be close to an asymptote. So what's an x value that's very close to 1, but is smaller than 1, to the left of 1?
0.9.
Sure. Let's use it. Let's try 0.9. So punch that into your calculator. 2 times 0.9 plus 1 over 0.9 minus 1. A lot of people in the class, the earlier class, had a hard time with this because they weren't using brackets. So maybe we should do one together. You could either use your fraction button if you have one, or bracket 2 times 0.9 plus 1 bracket divided by bracket 0.9 minus 1. 0.9 minus 1. Did you get negative 28? Okay, good. Try some of these. Some of them I'm going to just write down. Some of them you might have a chance to try it. You do have to try these and make sure you're getting the right numbers. So even if you don't have time now, maybe do it later, because if you're doing this on your calculator, you need to know that how to use your calculator, right? So if you're just watching somebody else do it and then you go to try it yourself and you can't get the numbers, what are you going to do? And then, just ask and we'll talk about it. Oh, negative 28? Was it negative? What's even closer? Nice. Turns out that works out to negative 298. What's even closer? What's the pattern here? Gwyneth?
0.9999.
Let's just stick with 3 because I don't have the other one written down here. And this one turns out it works out to negative 2,998. What's happening here, folks? We are approaching the asymptote from the left. The graph is either going to do that or it's going to do that. Which one is it doing? The blue or the orange?
Orange.
How do you know?
Because it's getting, as it approaches the asymptote, it's getting small,
Larger negative, which is smaller overall, but very good. So these numbers are getting closer and closer and closer to 1. Do you see that? And these numbers are getting bigger and bigger and bigger negative. So this is going to like negative infinity is where it's going, right? Eventually. Well, not eventually because you never get there, but you know what I mean, right? So how do we write this? We say as x approaches 1, and careful, this is new. And that means from the left. Y is going to negative infinity. And then what if we do it for positives? What is a number very close to 1 but just to the right of 1? 1.1 would be like the equivalent of, of 0.9, right? Very nice. Turns out that gives us 32. F at 1.01, which is even closer, gives us 302. And F at 1.001 gives us 3002. So what's happening here as x approaches 1 from the right? Y is going to positive infinity, right? Now, we're not going to check 3 points every time. I like to do it once because you can actually see the numbers like increasing. So it's kind of interesting to see that, and you're thinking of yourself, I'm getting closer and closer and closer to the asymptote, and the number's getting bigger and bigger and bigger. And you can kind of see it in the numbers. But normally we're just going to use one number, or in fact, for vertical asymptotes, you don't even need to use a number. So I will show you that next. What's the horizontal asymptote?
2.
Good. Y equals 2. Horizontal asymptotes occur for large values of x. So what's a starting number that we could use that's a large value of x? We're going to do the same thing. We need to find some numbers and see if we can see some kind of progression or some kind of pattern. We'll start with negative 10. Use a round number. Does that sound okay? When I plug negative 10 into the equation of the function, so 2 times negative 10 plus 1, all divided by negative 10 minus 1, all divided by negative 11, I guess, I get approximately 1.72. What should it be getting close to? 2. It's supposed to be approaching the asymptote. That's not very close, right? So 10 doesn't get you too close. So what should we go up to? What should we try next?
100 or negative 100?
Yep, I like it. And turns out this is 1.97. And what do you think we're going to try next? Negative 1,000. And turns out this is 1.997. Okay, now we're getting close to 2, aren't we? Those numbers are getting closer, or pretty close to 2. So as x goes to negative infinity, because that's what we're doing. We're picking bigger and bigger and bigger negative x values. Y approaches 2 from above or below? Which one is it? Are those numbers above or below 2? This isn't a trick question. What do you think?
They're below.
They're below. So from below. Okay, so the negative means to the left or below. The positive is going to mean to the right or above. We'll do the same thing here. F at 10, F at 100, F at 1,000. And I get 2.33. Again, not that close to 2. And I get 2.03. Okay, we're getting closer. 2.003. Okay, we're getting very close. As x goes to positive infinity, y approaches 2 from above or below? Above. Thank you. Because those are bigger than 2, but very close to 2, but bigger than 2. If you are using numbers, I would say you use 100. For the horizontal, you have to use numbers. So negative 100 and positive 100. For vertical, you don't have to use numbers. I'm going to show you a trick to avoid it. It's a bit faster, but it requires some mental math. I would recommend using that one and that one. When we put 1.1, so 0.1 away from, we got 32. I mean, it's fine. It wouldn't be wrong to do that. You're going to get away with it, but it's not very big. I like to see a bit of a bigger number. I like to see getting into the hundreds. You know what I mean? If I'm punching it into my calculator. Any questions on this? Okay, we're going to do one more. So every asymptote requires 2 tests. You got to check from the left and you got to check from the right. You got to check horizontal asymptotes going to the left of the graph, getting big negative, and going to the right of the graph, getting big positive. Every asymptote requires 2 tests. So if you have 3 or 4 asymptotes, there's a lot of testing going on there. If I was doing it on my calculator, I would probably program it in. 2x, what was the last one? Was it minus 1? Plus 1? Over x minus 1. Right? I would program it into my calculator like that. Hit equals, and then do that little trick. Okay? Okay, what do you think we should do first for this one? We have to find the asymptotes, and then we have to start doing the testing. How are we going to do that? What does your gut tell you?
Do we have to factor the bottom one?
I think we are going to factor it. Okay? And in fact, I'm going to factor the top 2 eventually when we do full sketches. This is something you're going to have to do, but it's going to help with the testing. So I'm going to factor the top 2. So I'm going to change the top around so it's written in the right order. To factor the top, what do you think the best thing to do is?
Like as if it's a square or something.
Yeah, but I'm going to factor out the negative first so that I have a positive leading coefficient. Okay, now I'm going to factor. Okay. So now that I've got, where do vertical asymptotes come from? You You already want to be like everybody in here wants to start to be able to answer that question.
From the bottom,
The bottom when it's
0.
0. That's why we want the bottom factored. Can you now, just by looking at it, see where the bottom is equal to 0? That's what we've been doing for 2 units, so I hope so. Right? So somebody give me one of the vertical asymptotes.
-4.
So x equals -4. Yes?
X equals 2.
Oh, you gave me the other one. Good. So I need to leave a little bit of space. The other one is x equals 2. Good. So for x equals -4, what is... Now careful, it's trickier with negatives. What is a number just to the left of -4? -5 is too far, but you're right. You went the right direction at least. So how can we not go quite as far?
-4.01.
Nice. It's back. Like that looks like it's bigger, but that's to the left on the number line, right? Because of negatives. So don't let, if you get that mixed up, you're really going to muck yourself up. And when I punch that in, turns out I get -118. And what is a number just to the right of -4? But very close to -4?
-3.99.
Nice. And turns out that gives us 116. So we're only doing one test for each. And then I say, as x approaches -4 from the left, where does y go? And as x approaches -4 from the right, where does y go? So what's the answer? For the first one, when I'm approaching from the left,
Positive.
no, not positive. Isn't that number negative? Yep. So, whoops. So -infinity. You're just looking at the sign of the number. And then the next one goes to positive infinity. Good. Okay, now I'm going to show you a trick to speed things up. Most people should be using this trick. Some people might really, really not like it or mess it up sometimes. And if you've messed it up a few times, or like if it's kind of messed you up a few times, you might be like, I'm not doing that anymore because it's just not working for me, and that's fine. But like most people, I think, should be using this. So like it shouldn't look too weird when we do it, and it should be something that most people are capable of doing. I got to pick a number just to the left of 2, but very close to 2. It's positive now.
1.9.
Thank you. Now I'm not going to use my calculator. I'm just going to think about what would happen if I sub 1.99 into all of those. All these brackets. 1.99 plus 3. I'm doing this one first, right? 1.99 plus 3. Sorry, I'm getting all mixed up with my thing here. Is going to be positive. 1.99 minus 3 will be negative because the 3 is bigger. 1.99 plus 4, positive. 1.99 minus 2, negative. Just barely, but negative because the 2 is bigger. I have 3 negatives because I've got this negative as well. That counts. If I was putting in the calculator, that would count. I don't care. I don't care what the numbers are. I only care if it's positive or negative. So 3 negatives is going to be negative. And isn't this a lot faster than punching it into your calculator every single time? And that's why I say if you're going to be punching it into your calculator, maybe you do the programming trick. Okay, what's a number that's just to the right of 2 but very close to 2?
0.01.
Nice, 2.01. 2.01 plus 3 is positive. 2.01 minus 3 is negative. 2.01 plus 4 is still positive. 2.01 minus 2. Positive. This one flipped to positive when we crossed over the asymptote. They don't always do that, so you have to do this testing. You can't just assume it switches, but this one did. So as x approaches 2 from the left, y is going to negative infinity. As x approaches 2 from the right, y goes to positive infinity. So there's your vertical asymptote testing. What's the horizontal asymptote? We had 2 vertical asymptotes because we had 2 factors in the bottom. And you only have 1 horizontal asymptote, so there's 6 asymptotes total. It's -1. And I would wonder if you got it from that step when I rearrange, because it's kind of in a nicer order. The top step is probably just as easy. But again, like we've talked about before, you'll have expanded version and factored version, so you're going to get different bits of information from different parts, okay, different places. So the horizontal asymptote is y equals -1. For the horizontal asymptote testing, I'm going to say this over and over and over again. You need to use the numbers. You cannot use that trick. We need the value. We don't care if it's positive or negative. Horizontal asymptote is going to be close to that. So of course it's going to be negative. That's negative. Okay, so I don't care if it's positive or negative. I need to know what the number is. So do you remember what we used, what number we're going to use for horizontal asymptotes?
100 and -100.
Good. So just, you have to remember, always use these. We get to the test and some people say positive. Like, yep, but that doesn't matter. Good for you, that's right, but that doesn't help. Okay? So when I plug this one in, I get -1.02. And when I plug this one in, I got negative 0.98. See, they're both negative. Of course they are. They're close to -1. They're going to be negative. Now, what do they mean? As x goes to negative infinity, x is getting very, very large negative. That's when you're near a horizontal asymptote. Is -1.02 above or below -1? This is where that negative thing that messes with your head. Imagine it on a number line. Is it above or below? It's below. So y approaches -1 from below. As x goes to positive infinity, y goes to, is -0.98 above or below -1? It's above. So -1 from above. And when we start sketching, you're going to do all of this and do a bunch of other stuff, and then take all of those bits and pieces and put it together into one of those graphs that we looked at before. Any questions? Yes?
So when it's horizontal, it could be above or below, and does the negative mean below?
Correct. Here's some other examples of graphs. There's the one that we already saw. So I've got approaching from the left, approaching from the right, above and below. Let's go around this way. Here's one where they're both approaching or going down, approaching from the left and the right. Hold on, folks, hold on. Approaching from the left and the right, and both approaching from below. So it's only one vertical asymptote that time, so it's different. Here's another one, both up. Look what happens here. This one is from above. This one crosses and then approaches from below. So they can do all kinds of things. So you're not allowed to just say, oh, well, if it's doing this, then it's going to do that. No, you got to do the testing every single time. And there's a oblique asymptote. And we'll learn how to test around those, and it's even yet different kind of testing. And we'll learn how to do that after learning how to sketch the sort of simpler ones. We have to find the oblique asymptote and then do the testing.